Hello everyone, welcome to my YouTube channel. In this channel I will teach you mechanical engineering lessons like engineering mathematics, heat transfer and fluid mechanics. Now in this video I would like to talk about thermal resistance in Cartesian coordinates, in cylindrical, spherical and convection and radiation resistance. Okay, as you might know, the electrical current in electricity equals electrical potential difference over electrical resistance, and that we show by I delta V over R. Electrical current runs in the coils between potential V1 and V2. If we have a resistance like R, you might think of it as a lamp or something else. That's it. So by using analogy between heat transfer and electricity, we can find a relation like Ohm's law in electricity for heat transfer application that look like this. If we consider Q as a thermal, if we consider Q as a thermal current and delta T as a thermal motive or motive force, and take a R as itself, we will have this sketch. This is a point with T1 with temperature of T1, and this point has temperature of T2. The heat transfer rate is our motive force. Notice that delta T in this formula is T of big T and T of small. Another note that you should remember is that thermal resistance arguments are in a steady state condition, and second, it has no heat generation or consumption. And the third one, it is one-dimensional. First, thermal resistance, we have Cartesian coordinates. Consider these two valves with a temperature T1 and X at X1 and temperature T2 at X2. We have Fourier's law that look like this. Q equals minus K A dt over dx. If I move dx from this side to this side, Q dx equals minus K A del dt. And by considering our boundary condition at x1 and x2 and T1 and T2 and T1 at these two valves, we'll have an integration. It is two differentiation. It is a normal ODE. You can easily integrate from x1 to x2. Q dx equals minus K, equals T1 to T2 minus K a dt. Okay, as it is a steady state and we have no heat generation or consumption, q comes out of the integral, and it is a Cartesian coordinates. A is constant, and also k is constant, assumed to be constant. This comes out of the integral. Q, and it is a simple math. x2 minus x1, x2 minus equals minus ka t2 minus t1. Okay, again q delta x minus ka delta t. Then we will have, okay, as t1 is bigger than t2, I put it upper here, upper than t2. We can cancel out the minus sign. It will become plus, and then we will have q equals delta t over delta x over ka. And if you have a comparison with a formula that we had earlier, q equals delta t over r, it shows that this term is r of Cartesian, in Cartesian coordinates. For thermal resistance in cylindrical coordinates, we have this figure. One cylinder inside another one, it's bigger. Okay, by using again the Fourier law, we will have minus ka dt over dr. Because it is cylindrical, we will have r phi and z, r theta and z. Okay, I move it here, q dr. A, or surface of the side surrounding, is 2 pi rl. L is the height of our cylinder. Okay, by substituting, we'll have k 2 pi rl dt over again dt. Okay, I move this r here and begin integrating. It's r, so I put r1 to r2 q dr over r. It's t, I put t. In r1 we have t1 minus k1 integration from minus k 2 pi l dt from t1 to t2. Again, q is a constant because we don't have heat generation or consumption, and it's a steady state condition. And k is a constant. L pi r constant comes out of the integral. It becomes an ln, natural logarithm, if we integrate. So we have q ln of r2 over r1. It's a definite integral. Okay, we can again cancel out the minus because of it becomes delta t. Again, k 2 pi L delta t. Okay. If we arrange this equation, we'll have q equals delta t over ln of R2 over R1 over 2k pi L. Again, if we have a comparison with our original formula, the analogy, it shows that this expression, it's the R of cylindrical. It's R of cylindrical coordinate. That's it. For the third one, we have thermal resistance in spherical coordinate. Again, by writing down the Fourier's law, we have minus k q equals, we have q equals minus ka dt or dr again. And in spherical coordinate, a equals 4 pi r2. It's the surrounding surface. By substituting, we'll have, and moving dr to this side, q, and r2 to this side, q dr over r2. It's in inside, a comes here, minus k dt. Again, by integrating and considering the boundary condition, R1 to R2, Q is constant, dr over R2 minus K is an assumption that to be constant, T1 to T2 d of t. You can bring it up to become r to the power of minus 2 and integrate. If you integrate, it will be q times 1 over r1 minus 1 over r2 equals k times t1 minus, then we have q equals delta t over excuse me, I forgot the 4 pi. I write it down. 4 pi, again 4 pi k. Okay, delta t, this comes in the numerator, 1 over r1 minus 1 over r2 over 4 k pi. Again, by comparison to our original formula, it will be resistance of spherical coordinate. Okay, for thermal resistance of convection, consider a solid plate and an environment which it has temperature of T2 and thermal coefficient of convection of H. By using Newton's law of cooling, we have Q equals H times A times T1 minus T2. Again, by moving to this side, we'll have Q equals delta T over 1 over HA. And by making a comparison between our original formula delta T over R, this is R of convection. 1 over. For the fifth one, we have thermal resistance for radiation between two solid objects. By using Stefan Boltzmann law, we have Q equals sigma A T to the power of 4 T1 to the power of 4 minus T2 to the power of 4. By using simple math, we open it up. It says mathematical relation sigma A T1 to the power of 2 minus T2 to the power of 2 times T1 to the power of 2 plus T2 to the power of 2. To reach the T1 minus T2, that is our original formula. Again, we open this up. This sigma A T1 minus T2 times T1 plus T2 times T1 to the power of 2 plus T2 to the power of 2 and call it delta T. We'll have delta T over 1 over sigma A T1 plus T2 times T1 to the power of 2 plus T2 to the power of 2. That's it. And by making a comparison with this formula, it will be our R of radiation, our thermal resistance for radiation. Okay, let's solve an example. It is said that find heat transfer rate through the valve. As we take a look, it is a numerical question, and it is shown that to be 3D, but we solve it in one-dimensional and in the direction of heat transfer from higher temperature to lower, as we take a look at. Okay, firstly, I draw a diagram of resistance. This is R of A, this is T1. These B and C are parallel. R of B, R of C, that comes to R of D. All of these alongside each other are in series, T2. Okay, as it is Cartesian coordinate and one-dimensional, we use our main formula, which was R of Cartesian equals delta X over Ka. Okay, for the resistance of A block, we have delta X, which is 3 times 10 to the power of minus 2 to make it in meter unit, and K equals 30 times A. which is 5 times 10. It's going through this surface. 5 times 10 times 10 to the minus 4 equals, it will all cancel out, 1 over 5 degree of centigrade over watt. It is the unit of R, or resistance. R for B block is 5 times 10 to minus 2 over 100. 100 times 5. This is 5. 5 times 5. 5 times 5 times 10 to the minus 4 equals 1 over 5 degree of centigrade over watt. R of C equals, again, 5 times 10 to the minus 2 over 5 times 5 and K is also 50. 5 times 5, 10 to the minus 4. It will be minus 3, 10. This comes out 10 over 2 over 5. 2 over 5 centigrade over watt. R of D, we have delta X, which is 2 centimeters, 2 times 1, 10 to the 2 minus 2, over K of D, which is 40, times, again, 5 times 5. Oh, excuse me. 10 times 5. 10 times 5. 10 there, 5 times minus 4. Again, if we cancel this, minus 2, 1 over 10 degree of centigrade over watt. In the next step, we should combine these two resistance into one. As it is a parallel resistance, we use it in electricity. R of BC is equivalent R of B, R of C over R of B plus R of C, which will be 2 over 25, 3 over 5 will be, we simplify 5, 2 over 15. In the next step, we sum up the RA, R of BC, and R of D to have the overall resistance. We have 1 over 5 plus 2 over 15 plus 1 over 10 to get 13 over 30 Celsius over watt. So our desired, our desired value will be delta T, which is 360 minus 100 over 30 over 30, which will be 60 watt. Okay, as the last example we have, it is said to be a very thin transparent heating element is attached to the inner surface of an automobile window for defogging purposes. The inside surface temperature of window is to be determined. We have given this figure and thermal properties inside and outside, and the geometry of window and its thickness and its thermal conductivity, and it is said to be find T1. Okay, we consider 5 assumptions to solve this question. First one is a steady state operating condition. Second one is a one-dimensional heat transfer through the window, and thermal properties are constant, and the other one is that thermal resistance of heating element is negligible, and thermal resistance by radiation is also negligible. Okay, by using thermal resistances, we have three kinds of thermal resistances: R of H, R of K, R of Cartesian K, and another R of H. We write it down. R of inside, it is 1 over HI dar A, and R of window is in Cartesian format, and delta X or L, simply we write L over K of window times A, and R of outside is 1 over H of outside times A. I sketch the resistance, which is series 1. This is R of I, R of window, R of out, T1, and T of outside. It's T of inside. T1 lie down here. Okay, by using energy balance, we write down the energy balance equation. We have delta T over R of I, delta T, T of I infinity minus T1 over R of I plus Q dot of H times A equals, this equals outside. T of 1 minus T of outside infinity over R of window plus R of outside. Okay, it is just a substitution, and the problem has been solved. Okay, we substitute our formulas to the equation. T of I infinity minus T1 over 1 over HIA plus Q dot of H times A equals T1 minus T outside over R of window L barrel over K window A plus 1 over H outside times A. It is cancelled out from our equations, get rid of it, and leftover is just substituting their numbers. 22 minus T1 over 1 over 50 plus Q dot of H equals T1 minus 100 minus 5 L, which is 5 times 3 to the power 3, K of W equals 1.2 plus 1 over 100. You can give this equation to MATLAB or ES to solve. If you do that, you will get T1 equals 14.9 degrees Celsius. That's our desired number. It was a beautiful question and applicable. Very good. Okay guys, if you have liked my video, feel free to subscribe to my YouTube channel. Just click on the subscribe button below this video. Have a nice time. Goodbye.